Um, Hello everyone, my name is Okoth Victor and we are here for machine learning. So today we are going to be presenting the models we did based on our EDAs, but I'm going to first take you through the EDA and everything we did. When you look through, we are going to talk about related work, problem statement, the research contribution, methodology, the description of the data, the results and the conclusions. Our background and introduction. So our project mission is to build a cultural conditioned digital elder that preserves structure and adapts African moral stories for modern learners. So our related works or the recent trends. When you look at the transformer era, modern architectures, Afrocentric NLPs, bias and representation challenge, knowledge structuring and progress, emerging trend. The field is shifting from universal or one-side AI towards a cultural condition sovereignty aware AI systems grounded in local knowledge traditions. Now for this, we shall look at our problem application, the domain application problem. Like the African moral knowledge is mainly oral and not sufficiently digitized in the structured form. The traditional narratives are culture rich but vulnerable to loss in modern digital ecosystems. Current AI systems are non-culture grounded in African moral frameworks. There is no scalable digital elder mechanism to preserve and adapt these narratives for modern learners. Education access to authentic culture, faithful, moral content remains limited. For this, we are able to come up with our research questions and objectives that will help us. How can African moral narratives from heterogeneous tradition sources be cleaned and structured in an AI already dataset? What linguistic and thematic patterns emerge from EDA of the cleaned corpus? Which transformer-based models provide the best baseline performance for the culture-grounded moral text classification? Then for this, we are able to come up with our objectives. Build a reproducible pipeline to ingest, clean, and structure African moral narrative texts, to implement and evaluate loadable learning strategies suited to scarce annotation settings, produce a dataset and modeling foundation for a future digital elder story generation system. From this, our research contribution, we curated and consolidated a multi-source African moral narrative corpus from traditional knowledge books, designed a reproducible text cleaning and structuring pipeline tailored for folktale style data noise, produced an analysis-ready dataset with traceable document level metadata and engineered features. The research outputs, we are going to have a cleaned corpus of African moral narrative in text, a structured analysis artifact, EDA notebook, training notebook, and a documented methodology foundation for the next phase. The systems architect is going to have three phases. We are going to have the data engineering, the analysis and learning, then the output and the impact. In the data engineering, we shall have the data sources. We shall also have the data ingestion and standardization, the pre-processing and cleaning, also the dataset structuring. Then in the analysis and learning, we shall have the EDA and the quality analytics, the unsupervised modeling, low-level learning. Then in our output, we shall have the transformer model trainings, whereby we are going to be looking at our models, also the narrative, the moral narrative classifier, which will be like our final product. When we talk about the data description and the EDA analysis, our data contains 17 text files collected from the African folktale or the traditional resources. The data is in the text. It is in the text. Then the initial schema of our data, it is the doc ID source file raw text. Our data has no empty documents. There are no duplicates. Yeah. Then we were also able to produce 25 visualization across the lexicon, structure, sentiment, and thematic dimensions. Document the lengths, are highly heterogeneous. Then our corpus is complete and non-duplicate but initially contain non-narrative structured noise. After controlled cleaning and the dataset became analysis ready, revealed meaningful thematics. Then, for our output resources and discussion, we cleaned our data, as I explained. Then we made 25 visualizations. Amidst this visualization, we had a what? We had the distribution of word counts. For this, it shows a wide spread of document size and right scale distribution. This matters because long files can bias feature statistics and model behavior, so we interpret the results with length imbalance in mind. For also the lexo diversity distribution, this one shows that the lexo diversity is not uniform across documents. Some texts are vocabulary rich, others are more repetitive. This indicates that the narrative complexity is multidimensional, so we need multiple features to represent the corpus properly. Also, the expected results, when you talk about the unigrams and the top bigrams, these ones highlights the most frequent words across the corpus. This capture the recurring narrative and the moral vocabulary. From this together, these plots show repeated moral linguistic patterns that can support weak labeling and thematic interpretation. When we talk about our SDV projection and the cluster size distribution, for the SDV, this one places documents in the latent semantic space, documents that are close and more similar in context. Then for our cluster size distribution, it just shows how documents are distributed across the k-means clusters. So the combination suggests that the corpus has meaningful internal structure which supports unsupervised groupings. Our expected results and discussions, we have the heat map. The heat maps that we are going to show, I'm showing you. Many documents activate multiple topics indicating mixed moral and culture themes. Agreement between the LDA and the NMF increases confidence that these latent themes are real and useful for future story conditioning.
Hi everyone, my name is Yohana Muhammad. I'm the second presenter. I'm going to talk about the model overview. This slide presents an overview of the different models used in our project. Categorized by their function, we have transformer-based classifier including XLM Robata and Debata V3 and MBAT for supervised learning. For embedding and topic modeling, we use sentence, bath, and bath topic. Finally, long format is included to handle long narrative sequences that exceed the standard 512 token limit of traditional transformers. Each model was selected for its specific strength, multilingual understanding for representing an interpretable topic discovery. Here you have the XLM, Robata, and Debata V3 training setup. In this study, we trained two transformer models, XLM Robata base and Microsoft Debata V3 base. The task was test classification using a weakly supervised dataset of more narratives. We train on the first half of the data and fine-tune on the second half. The models minimize cross-entropy loss using the Adam W optimizer. Evaluation metrics included accuracy, macro-Evans score classification, reports, and confusion matrices. This setup provides a reproducible, low results baseline for classifying culturally grounded moral narrative. Then here you have the architecture of the first model, XLM Robata. Here it is a transformer encoder. The input narrative is first tokenized into subword units, then converted into embeddings combined with positional information. This passed through multiple transformer layers with multi-self attention, feed-forward networks, residual connection, and layer normalization. The final representation is aggregated, typically using the CLS token or pooling, and paste to a classification head with a softmax layer, which output probabilities for each model category. Then you have the architecture of DBATA V3. Here, improves up on standard transformers attention mechanisms. It separately encodes content and position information. The input is tokenized using sentence space or BPE, then embeddings and created for both content and position. This pass through transformer layers with self-attention. The output is aggregated and passed through a classification head with softmax to predict model category probabilities. The last here you have a macro F1 comparison for the two models. So this slide compares the performance of XLM Roberta and DBATA V3. XLM Roberta outperformed DBATA V3 in these settings. However, overall performance is low due to limited training data. The confusion matrices show that both models struggle with minority classes. For example, DBATA V3 only predicts compassions and misclassifies all other categories. XLM Roberta performs slightly better but is still showing significant class imbalance issues. The macro F1 scores for XLM Roberta is 0.14, while DBATA V3 scores 0.00, indicating it failed to predict minority classes at all. Then here you have the purpose of explainable AI. The XAI component was designed to edit model behavior beyond simple performance metrics. At the global level, we use techniques like cost analysis and classification, report, interpretation to identify systematic patterns. The audit revealed that both models tend to collapse towards dominant classes instead of learning minority categories. This indicates potential bias and overfitting. The table shows identical hyperparameters for both models. Then the XAI findings help us understanding why predictions are made and reveal that the current error patterns are driven by data quality issues rather than model architecture alone.
Okay, so now talking about the long former and the MBAT models. So when I talk about the long former and the MBAT models, in this study, the transformer-based language models we use to analyze, classify the moral narratives from African traditional knowledge, specifically the MBAT and the long former. They are employed to capture semantic meaning from the collected folktale text. Long former is useful for processing long narratives because it uses efficient attention mechanism that allows the model to handle long sequences without excessive computation cost. Meanwhile, the MBAT enables multilingual understanding by learning shared linguistic representation across many languages, which is valuable when dealing with cultural diverse text. Together, these models support the extraction and the representation of moral themes from traditional narratives, contributing to the development of a cultural conditioned AI system capable of preserving and generating African moral stories. Now, I'm going to talk about the structure of the long former. Long former, as we know, it is a transformer encoder designed from long documents. It replaces full attention with sparse attention, allowing much longer text context windows. The input is tokenized, encoded through sparse soft attention layers, pulled and passed to the classification head that outputs moral category probabilities. Now, the structure is that in the long former we input the text. After we tokenize the text, we do the embeddings. After doing the embeddings, we do a sparse soft attention encoder, which is the long former. Then we do a pull, then the classification head, then we can get the softmax. In the embeddings, we are converting words which were tokenized or categorized, let me say, into long former. Let me say it is 1, 2. Then the embeddings, we encode the long former into a given numerical value. When you talk about the MBAT, for MBAT it's a multilingual transformer encoder. It tokenizes text into subwords, encodes them through standard self-attention layers, then uses a classification head on the pool representation to collect moral categories via softmax. For here we are doing the input text, the tokenizer, the embeddings, the transformer encoder, the pooled CLS, a classification head, and the softmax. As we all know, for the tokenizer, as I said, we are separating words such that we can give them a numerical value when we are doing the embeddings. We can say that in the long former confusion matrix and the MBAT confusion matrix, the long former outperform the MBAT in this setting. So the performance is low due to the small data, the weak labels, and the class imbalance. Then, when you talk about the purpose of the explainable AI, the component was to audit the model behavior beyond aggregate performance metrics. Then the audit revealed that the models tend to collapse towards dominant patterns under class imbalance, while monitoring class reliability remains weak. The AI finds explain why predictions are made, expose failure modes caused by weak labels and small sample size, and provide direct guidance for the dataset improvement priorities such as better annotation. Overall, we can see that the XI analysis indicates that the current errors, they are primarily driven by data regime constraints rather than architecture alone. Yeah, those are the two models I was able to make, and their architecture as provided below. Thank you for listening.
Hi, once again, I'm going to continue the presentation for the multilingual ES plus K-means and BAT topic modules. Here we integrated two unsupervised modules for semantic analysis. First, the multilingual ES generates dense vector embeddings for moral narratives, capturing semantic meaning across multi languages. These embeddings are then grouped using K-means clustering to identify semantic clusters. After the second is the BAT topic. It performs topic modeling by combining embeddings with existing techniques to automatically identify meaningful terms. Together, these methods help uncover thematic structures and organize narratives according to shared cultural and ethical concepts without requiring label data. Here you have the architecture. For the architecture, this diagram illustrates the workflow. Text chunks from our narrative corpus are passed through the multilingual ES embedding model, which converts each into a semantic vector. K-means clustering is then applied to these vectors to discover latent clusters of similar moral narratives. The output is cluster labels that groups semantically related stories. Then after you have the architecture of the second module, which is BAT topic. It follows a similar but more sophisticated workflow. They are converted to embeddings, then clustered. However, BAT topic additionally extracts representative words for each cluster using a vectorizer, producing interpretable topics description. The final output are topic words that describe each term and topic frequencies, showing how common each term is in the corpus. Then here you have the visualization. This slide shows two visualizations of our unsupervised analysis. One, on the left, the topic frequencies bar chart displays how many documents belong to each discovered topic. Topic 0 is the most frequent with nearly 2,000 documents. On the right, a UMAP 2D projection shows ES embeddings colored by K-means clustering assignment. Each color represents a different cluster, and we can see how narratives group together in the semantic space. This confirms that our unsupervised methods successfully identify coherent semantic structures in the data. Then here you have the purpose of the explainable AI. The component also applies to our unsupervised models. The explainability score is calculated as the average of individual instance scores across the dataset, ranking from 0 to 1. Higher scores indicates greater transparency. The table shows hyperparameters for BAT topic and multilingual ES, which has 3 inputs and the rest also of the hyperparameters. Then overall, the XAI analysis indicates that current error rates are driven by data characteristics and algorithms, features rather than architecture alone. Here to finish, the models that we train are necessary. They provide the analysis and control layers for our project. The classifiers, we have 4 models. Then they learn to recognize moral categories from narrative, while the unsupervised models reveal latent terms and structure without labels. Together they help clean, organize, and label the corpus, which is essential for building a reliable training signal. The final step will be to train a generative model on the clean, structured, and labeled narratives, so it can produce cultural grounded stories with controllable motions. And then here you have our conclusion. In the conclusion, we successfully transform heterogeneous raw African narratives into a clean, structured, analysis-ready corpus. Our EGA pipeline, with over 25 visualizations, reveals clean linguistic and thematic patterns. Unsupervised analysis confirmed these findings. We implemented and tested a low-level learning setup with strong transfer learning baselines. However, for the limitation remain, cultural nuances are not fully captured by generic sentiment and keyword rules. Long narrative structures are translated, affecting performance stability. Current labels are weak or heuristic. Introducing noise, class imbalance significantly impacts macro level performance. Despite these challenges, the project delivers a solid technical foundation for the next phase, cultural technological folklore generation, the digital elderly. Now for our next step. The next work includes several key directions. First, expand the dataset with additional African folktales, proverbs, and oral narratives from more regions and languages. Second is to build a gold standard annotated subset with expert validation and more categories. Third, improve low-level learning using iterative pseudo labeling and active learning loops. Fourth, instead model benchmarking with long context embedding approaches like long format and substantive alongside our current baselines. And the last point will be to develop a control generation module to produce cultural grounded knowledge stories. Now for the acknowledgement, we sincerely thank our course lecturer for academic guidance, feedback, and project direction throughout this work. We also acknowledge the open source NLP communities and tools that supported the research, including the developers and Hugging Face transformers. Thank you.